Brandon, as well as all the great help that he gives us with webcasting these events and at Bogons, amazingly he also has a day job at BBC. And Brandon is going to be talking about some of the BBC R&D work that they have been doing at the recent Commonwealth Games in Glasgow.
Roll video to start with. Roll video. So that's just a few pictures of what we did this summer. There's more stills that you can see better in some of the slides as we go through it. So we've been doing lots of work, obviously, on the internet and TV. We're starting to feel that we need to get these things together. And that started a project that we're calling IP End-to-End. The difference between what we've done before with broadcast and what we're doing on the internet has always been, broadcast has been a one-way medium. And we broadcast things on the internet, and they are really separate things. It's just a recreation of that old world. When we think about actually what happens when you put these things together properly and you stop bothering with all the old TV technology and move it to all IT-based stuff. And in that IP world, it's not just that traditional broadcast stuff. It's bringing tailored content. So rather than saying everybody gets the same thing, you can send things more applicable to certain devices people have, or the use or circumstance or location. There's also all the Internet of Things stuff to think about, how you use other people's environmental data in the production of TV and so on. And there's user-generated content, actually using a return channel for something for a change. I think that was fairly obvious. The easy thing to do to make TV work on the internet is to move all the broadcast to IP. So we took over Glasgow Science Centre for the summer, just one room of it. It's right next to Pacific Quay on the top of the picture. The building on the left is BBC Pacific Quay, which is studios there. The building on the right is Glasgow Science Centre. The picture underneath is inside the Glasgow Science Centre. I keep wanting to call it Glasgow Space Centre because it's got a very big pointy thing outside, looks like a rocket. And we're showcasing a bunch of things. There's quite a lot of demonstrations of other areas of work we're doing. So that's better. The primary thing was to show IP end-to-end, covering the games in UHD 4K. It's not quite 4K for TV, cinema's 4K. Yeah, I'll stick to this. So the IP end-to-end stuff first. That's about taking IP out of a camera and getting it all the way to the end user and all the processing in between and staying in the IP realm. At the moment, video is a mixture of serial digital signals, then it goes into devices, some of which may process things in software, some in hardware, and eventually you end up with something that's a mixture of hopping out of different technologies, all dedicated and expensive. And although they are a commodity now and getting quite cheap, they are the old world of one way and everything's dedicated hardware. So you want to put a building up for these things, you have to put lots of coax in there. And it's getting increasingly difficult with 12 gig SDI to actually get this coax to work. It's about time they move to fibre. And we have suggested that actually even if you don't want to take the Ethernet layer, just move to the fibre. That would be a great start rather than trying to get all this coax that was designed to go at 270 megs way back and trying to get it to go at 12 gigs, which requires quite a lot of effort in the silicon, which is why they're only just starting to do it. And that's what's required to do 4K on that. So at the moment, a lot of the stuff is done by running 4 existing 3 gig SDIs in parallel. So you end up using 4 times as much cable infrastructure. And at the moment, the 4K is only thought to be 50p at the most. And the problem is you need to be faster than that. So it's really not 12 gig, it's beyond 12 gig that you really need to do this stuff. And one last bit of it is actually the end-to-endness of it. And what we didn't want is to go through just the traditional coding unboxing and then deliver the same stream to everybody to each home. We've actually done in this phase of it, delivered the same stream to DTT and to the home. But that's to show that you get the same quality regardless. It's not a world where the internet is a lesser thing and you give it half the bit rate or whatever. This is saying actually this is going to take over from TV broadcast, mostly because they're going to nick all the spectrum for LTE and things, and partly because when you want more channels and need more bandwidth, the only way you're going to get it is across the internet. So in doing this, we did some firsts. This is the first time that anyone's managed to get these things going together, multi-camera, IP end-to-end, particularly for sports and things where they usually don't like trying anything that's new because it might break and it's all live. It's not like you can retake it. Obviously it's the first Commonwealth Games in UHD because that's they just made it for this one, and the end-to-end stuff is first as well. Most stuff is usually round trip through SDI at some point, and the point of this is all the processing is done in software, so we don't need to. Quick diagram showing where the stuff is. There's some stuff in the north, in Glasgow, which is where all the production is taking place. There's a metro network around Glasgow, or was, it's all historical now. There's a metro network around Glasgow between the various venues and Pacific Quay and the Science Centre. Some stuff in Salford and some stuff in London. Salford was mostly, all three locations have demonstrations, and some of them are actually contributing to the production. Particularly in London, all the audio was produced in London. So a major part of the IP studio part of this work is that you don't have a single studio anymore. You have a virtual studio where any of the components can be anywhere. We didn't have to put the audio in London, but it seemed like as good a place as any because that's where we had some space for it, and you're supposed to be able to put this stuff anywhere. So the signal we're capturing is just regular. I'll look at it to, you notice it says 2160p50. That's actually what it's really called. It's not really called UHD or 4K or whatever because we count it differently. That was captured, which is 12 gigabits, compressed down lightly. We actually made multiple bit rates because part of the production is that not all networks are equal. In the normal broadcast world, you can work with proxies, but that's mostly offline. Usually for live productions, they work with the actual signals because they're worried about latency and timing and all sorts of things, and they want to see what they get when they press a button is the thing that comes out. This is about showing that actually wherever your network is, you can still handle that world because we've arranged all the timing so that if you press a button, when you see the feed you want to change on a 100 meg stream, if you're looking at a proxy, that same timing gets reflected back to the 4K that's switched in some data center somewhere. So it just works as if it was a regular traditional broadcast system. It's just that we've abstracted all the features they require into an IP world and made them work slightly differently to suit. The streams are there's actually two sorts of streams. There's a live multicast, which is the main stream, and there's also some HTTP stuff that's used for background transfers from the capture nodes back to the studio, so we can actually record this stuff. In case there's any disruption of the multicast, we've then got a clean recording as well. And also those HTTP proxies can be used for viewing on offline devices or iPads or whatever. It's distributed production, I said. It doesn't matter where any of the things are, where the production people are, where the cameras are, where the consumers are. As long as you've got a good network between them, it's fine. And I've already mentioned the multi-resolution working, where not everybody could get 4K. And in the Glasgow Science Centre, we could get 4K there. But rather than spending money on big expensive screens, we wanted to prove the point that that production gallery that's going to be there was HD. It didn't need to be 4K native everywhere. You could work with the proxies and the effect is the same. We could have put it 4K everywhere, but it's just ramming on the point that these things don't need distributing everywhere. You can work with a lower grade network in some locations. Everything was IP, so it wasn't just about moving the video. All the command and control and reverting and things you normally get in there. So it's basically as talkback systems. We didn't have time to build one for this, so we actually nicked Mumble from the gaming community, which is quite good. If you can play Call of Duty with it, you can probably control some cameras. And camera tallies and things, the reverters are over IP, so the light comes up on the camera showing which one's live and that sort of thing, and other metadata gathering from the camera. At some point, and this is starting to happen in the real world already, we asked a few years ago, camera manufacturers, Sony and Canon and everybody, so actually what we really want, instead of putting a box on the back of the camera to bundle up all the signals that come out of the camera and turn them into IP, it'd be really great if they all came out native in one connector on the camera. And we made a box called Stage Box that bundles them all together to show what we wanted, but it's really about saying actually that's stuff that should be in the camera, and that's starting to happen. Sony and various others are starting to put various degrees of IP in the cameras, get some Panasonic cameras where you can suck out a feed over Wi-Fi and things. So people are coming around that way thinking. It's generally consensus is IP is going to be in all these devices, just a question of how much and when. And all the we didn't build any special devices for controlling it. Normally you have a dedicated desk for these things, and they're quite expensive to build. So all we did was took a touchscreen PC and made a web interface for it and made a software switcher. So all that did was use web services to tell the various devices on the network when to switch video. And rather than have some dedicated hardware, it's just quick lash up in software in a web browser. The output formats were not. Well, we did have some regular 264 going around, as I mentioned in the earlier stuff, but part of the future delivery is HEVC is coming along. It's going to be the future codec for all these things. It's starting to appear in a lot. If you buy a 4K TV, quite a lot of them have HEVC decoders in them now. They're not necessarily, they don't necessarily tell you that because they don't know how well they work and whether it's going to support all the features when the services come about, but potentially some of these can receive these services now, so you don't necessarily need a set-top box. And the Freeview sets we had receiving this, they were using the built-in tuner inside the TV. And yeah, some details of that. Basically, you end up with a 35 megabit stream of HEVC, first generation encoders. So they don't deliver the 2-to-1 in performance improvements and things everyone normally claims. It's first generation, get it working technology. So we're glad it worked. We'll worry about the next generation when we get the bit rate down. But still, 35 megs for a 4K stream is not a bad thing. You know, you can get it over a BT fiber cabinet type service. And as part of this, BT were doing just that. They were delivering this to some consumers over their regular service via their CDN. Some pictures of the place. They built some quite shiny buildings around Glasgow for this. It was all very nice. And it was fun lugging racks of equipment into these things. As we only had a few sets of equipment, we had to lug them between venues, between events as well. So it was fun trying to get these things in. Normally, these things are just rigged and people roll up and use them. And we had to de-rig and re-rig in other locations as we were going along. But it works fine. We're mostly up in the gods for some of them, as you can see from the top picture. And in that particular venue, we had one camera at the ground level as well. The rest of the broadcasts are quite protective of the good positions. So it's quite hard to get the really good shots down there because all the major broadcasters have got them already. When I say major broadcasters, it's a bit like the Olympics, where they have their own broadcasting service in there and you take the feeds that they give you. So it's not fair to blame the other broadcasters, it's just they've been bagged for the other broadcasters by the host broadcaster. In the Science Centre, that's the production gallery. So you may have seen a normal TV studio which has a desk with loads of knobs in there and loads of screens at the far end. Didn't have one of them, it's too expensive. This is what you need for software, the bare minimum usable system. You know, the middle screen showing all the various camera shots you got, one showing your output. The bottom right shows the control surface, which is just a large touchscreen PC, and you just touch the buttons to do the switching. And it also shows, you know, you can't see it's got microphone things for all the command and control. So he's directing all of the cameramen around the place from there and deciding which feeds to take. It's just a close-up of the same thing. So you've generally got the director on the right, someone on the left as assistants, which is setting up shots and things like that, making sure all the resources he needs is available when he needs them. That's the London part of it, not much to see, it's just a little studio with audio mixing and things, but it was totally separate. This is what you wanted to see, racks of equipment. The most interesting piece of equipment in there is second down in the left-hand rack, which is time server. All the synchronization for all this is done with PTP. We're working with SMPTE and a bunch of other people to get that to be the timing standard for all future broadcast. And that's issues because it's work in progress, but we're working with Cisco and a bunch of other people on doing that, so they're interested in this as a trial. There's interesting issues and things to work out depending on your switches. We're using a lot of the Catalyst 3K stuff, which does luckily support to a degree that the PTP functions were required. But still, we had issues of when we had to do where we could put a boundary clock and we couldn't actually distribute it around all the metro nodes. We ended up with one switch in the middle having to be the boundary clock for all of the other switches and devices on them. Below that is the routers, ASN9K. Just above that is the optical amplifier from Cube Optics that we used, some servers on the right. So that's not a very good picture of the network, but it shows you roughly the sort of things that are in each of them. The fibre in the metros was provided by Virgin Media. They provided us dark. They provided it on a better lead time than anyone's ever had ever. And use this as a reference if you want them to move quickly. Say, well, you could do it for the Commonwealth Games. Why does it take a year to put fibre into Manchester? The main backbone of this is Janet. We couldn't have done this without them. I'll get on to more of that later. Obviously there's a few more bits that involve Cisco in there because Cisco were a major part of this. They had one of the demonstrations at the site as well as loaning us the routers for this. And BT and Archiva are involved in distribution part of BT to the fibre to camera stuff and Archiva for DTT. Although it's intended to be IP only, we wanted to show that it's on parity with broadcast. So we took over a DTT MUX, 3 of them, one in Scotland, Manchester and London, and put this out. And for the stream we're doing, it took an entire MUX. So normally you get half a dozen or more channels in there. So you can see it's going to be a bit hard if we want every channel to be able to do this eventually. We're going to need more spectrum, or we're going to need to make Freeview way more efficient. And we have had suggestions for how we do that. When we did the switch over, we said, well, if you're going to switch all these boxes out, why not move to MIMO? And then we can have some more bandwidth out of it. But unfortunately, they didn't like us having to change every aerial on every house in the country. Which is a shame, really, because you need to do that eventually. So, quite a lot about the network. It's all down to Janet. We do have plans to do a lot more. Originally, when we're doing this, we're actually thinking the future is more bandwidth. So you do have to do everything uncompressed. That's how studios work at the moment. If you want parity with current studios, you have to have uncompressed for it. We did plan to have uncompressed, basically 12 gigabit streams flying everywhere up and down the country. And we were going to take some waves off Janet and link all those nodes up, and it would be an entire dedicated network for this. Unfortunately, when we were talking to Cisco, there were a few potential snags in the equipment they wanted to lend to us. They weren't quite sure if it could support 12 gig flows. Because internally in a lot of these devices, although they've got lots of bandwidth, they're made up of a lot of little lanes inside, and then they're aggregated, and then the data stripes across them in some manner. And that's the difficult bit, in that they wouldn't guarantee us non-out-of-order delivery of packets if we put a 12 gig single flow through it. And then there's the having to test that across Janet. There's quite a lot of things in there. Potentially, we could have done it, but we're out of time and money. So we did the next thing, which, given this network is supposed to be scalable in that you don't have to have tons of bandwidth to run an IP studio, we said, okay, well, we'll just move down to the next level then. We'll do it light compression, because we have various degrees. The rates that are generated are anything from 100 megs up to 12 gigs. So you can choose whatever level you come to with for the quality you want. So we did a lot of the production of this at 1.2 gigs for the main streams moving around. That meant we could actually plug into Janet's existing network, so rather than taking waves from them. Is that 10 minutes or 10 seconds? 10 minutes. Right. Yeah. We moved over to Janet's IP service. There were some worries from Cisco about whether Cisco and Juniper would play nicely doing 1.2 gig multicasts between each other and things, and when it all works together, it just worked flawlessly. As did Janet's network. Once we got past the next bit, which is we had real problems getting 10 gigs, 100 gigs working rather in some areas. Some of it was because the equipment just turned out to be faulty. But we got that fixed, and it turned out we still had some packet loss, and we couldn't actually find out where that was, and we were going to go live in a day or so. We did wonder, given that a lot of links were 20 kilometres and in London was 40 kilometres and we only had LR4 optics, we had to amplify the things, so we used cube optics, optical amplifiers. And we don't think they were the problem because in Salford there was no packet loss. In in London and Glasgow, on one direction there was no loss, so the things could work. It's just on one direction on each of those two links, Glasgow and London. We had some packet loss, lots more in Glasgow and less in London, but we couldn't get to the bottom of where it was and we ran out of time. Luckily in Glasgow, Janet pulled some tricks, and rather than doing it through all their distribution frames, various places around their pop, they ran some fibre across the floor and got us a few dB more room, and it worked without the amplifiers. So we can't say it was the amplifiers or the fibre, we think it's the fibre actually. It may have just been dirty actually, we're not sure what was causing it. It was just, background, slightly higher in Glasgow, lower in London, dribble, and we think that is fixable. That's just fibre, probably care and maintenance of it. I'll flip back to it for one thing. One other thing that was a problem with switching to IP is we didn't have layer 2 anymore, and for the LTE trial we're doing, we're required to get some signals from EE up there, and we tried doing LTTP v3, which would have been great for carrying those multicast things up to tunneled across Janet, but in the ASR 9K, it turns out it's not supported even though it's configured, and it just sits there doing nothing. And because you're doing multicast, you think, I must be doing something wrong it doesn't like. And it turned out it's just not supported. So we did a quick bodge to Ethernet over MPLS over GRE. Anyway, we got it working at 7 o'clock, which is just enough time to go live at 9 o'clock, isn't it? There was lots of people running around because the stuff hadn't had a proper end-to-end test because of the packet loss, so there was quite a lot of last-minute work going on, and actually throughout the week, because what we'd rolled out was not something as a tested system. This was the first time this had been put together ever, and first time the code had been tested in some configurations because it's all been tested in a lab in London, and they haven't tested it. What happens when you put some distance between the various nodes, and there were issues due to latency. That's just because people hadn't really figured out what would happen in certain situations. So it worked. We did 2 weeks there, produced all the stuff, stored it. There's quite a lot of videos you can watch on the R&D blogs. It demonstrated a distributed approach to production can work. We do it already actually, because you actually send a truck and a van, but people still like to send a lot of production staff to these events. And our aim is actually just send the cameras, everyone else can just stay at home. They might not like it because they don't get lots of expense and things, but actually overall, it's less grief than sitting in a field in Glastonbury and being in the back of a van rather than seeing the events. You might as well be in the office. So I'll show you a few pictures. Some of the other things are on. Besides the IP steering things, we're showing some of the other things that we'll do when we have IP end-to-end. Things that we can't do in the current system, which is from a 4K wide-angle camera, people can each steer their own view. So this is a bit like Google Maps. It produces tiles of video, and depending when you navigate around it, stitch them together in your browser so you can see a virtual view, so you can zoom in, move around, and everyone can do it independently without having to have a steerable camera each, which is the best way of doing a webcam. Oh, and one interesting thing is to remix the audio as well to try and make it match what you're looking at. Did some VR stuff, because that's the future, isn't it? It's been the future for a long time. The headsets and things are getting cheaper now that people are starting to look at it again. We're just having to play around with it and put up a 360-degree camera for people to play with. There's some other tech that actually starts to show the IP in there. Augmented video player does overlays that move around, show you what you're doing. There's a Cisco living room, which shows what the immersive experience is like, where you've got, rather than everything being crammed into the one picture, you separate out all the audio, video, the graphics and things and display them on various devices, tablets, on your wall to the left, on the main screen, around the picture. And that's part of the main thing we're going to get out of this is we're moving to a component-based delivery, basically atomized content. So you get in the games world, you deliver all the components that get rendered in the games console at home. I think actually that's probably more where the future of TV is going to be, in that you're sending basically a metadata stream to people and they pull all the feeds to the home and render them in the TV. And that means that they can do all sorts. Besides taking your feeds, it can be combined with all sorts. We did broadcast live over EMBS, which is LTE broadcast. That was the first, done with EE and Hawaii. Testing high frame rate as well. One of the problems with the higher resolution is you actually need a higher frame rate as well. It's quite nice to have high dynamic range as well, which we're working on, but the high frame rate is the key thing. One of the problems is if things move too fast, and we found this when we did the Olympics in 2012 with the 8K, in that if an object moved across the screen at 8K and took more than a couple of minutes, basically your resolution disappeared in motion blur because they were only doing it at 60p then. 100 Hz is about the minimum you need to get away at this sort of resolution with something that doesn't look horrible every time everything moves. Also, we're showing people some home distribution of TV white space, what the spectrum looks like around Glasgow and what other things they could get in there. We also did a DTT versus internet. It's 2 screens. The internet one looked best, but that's not because it was better, it's just because that encoder happened to work a bit better than the one used for DTT, otherwise they're exactly the same bit rate. In theory, should have been identical. But the people on the right seem to prefer the internet one anyway. Don't need to cover that. There's lots of stuff that's coming in the future. Mentioned the camera stuff, where we're going to try and get us into the future generation cameras. And that's it. Is there any questions?
Trev from Lonap. Very interesting, as usual. Just out of interest, has the BBC given thought to what kind of speeds access networks that consumers would have to access IP and this kind of technology, and also what its effect would be on the backhauls?
Yeah, I don't care. When we started doing video, it was all postage stamp things trying to go down modems, and it was really rubbish. And we did it anyway, and because we did that, people made the pipes fatter and things. And we found all through the evolution of iPlayer so far is, if you make it and it's rubbish, people make a better network for it. So you might as well just make it bigger rather than wait for the network to come along. Because the network only comes to accommodate what people are using it for. It's not built speculatively. So if people need bigger bandwidth, and there's a commercial model behind it, of course, then it will happen. And you can see with that what's happening today. BT and various other people are saying, we're going to do RTV over the internet. It's admittedly their private network, but the bandwidth is there. The only question is how much. And if you go to the major providers, their internal cost of backhaul is bugger all, whereas actually the retail price is quite high. So if you're one of the 5 bigs or whatever, then you can afford to do a lot of these things. If you're buying it off BT wholesale, then it doesn't stack up. Paying 50 quid a meg for a 35 meg stream is quite expensive compared to retail fibre to the cabinet. But that's today's cost model. These things need to evolve. And we're working with BT on the technology of this. We can't say what the market will do commercially, but this is entirely possible technically today. It's just a question of how you scale it and how you put a suitable commercial model behind it.
And do you have a perceived, what would the typical broadband speed have to be at home? When you consider that everybody in the house has got their own little, they're all streaming it on whatever the equivalent of the iPad will be by that time.
Well, the thing is, you don't send more than people need. If you're looking on an iPad, you don't need to send them 35 megabits. If you're looking on a 16-inch TV, then probably you do. Yeah. So we do that already. We do that already in iPlayer. If people are looking at it on a small screen, even though it's capable of something big, then we don't send them more than they need. But the assumption is that we're going to need probably 20 to 30 megs to do all of these things. So you're going to want something. If everyone had 50 megs, that'd be grand, wouldn't it? A gigabit better there.
Hi, Brandon. Jim Reid. Just got a very cynical observation for you. You said that Virgin were very, very responsive at getting cable put in. I wonder if that might have anything to do with the fact that Virgin were one of the key sponsors for the Commonwealth Games.
That may be related, yeah. And also they had free rein to go and dig wherever they liked up to go and do it. So I think they got around some of the permitting issues as well through that.
Brandon, did you have any issues with sort of transcoding and sort of feeding the 4K feeds out onto your other devices and sort of other distribution platforms?
Yeah, the HEVC encoders really were first generation and they kept crashing. And we found that actually when we did, if we do a cut of certain video going into them, that would crash them even though it's the same video signal. So we had to work around a few things and get a few things fixed as we went along when we found out what upset them. But generally, they were pretty reliable for a first generation, fresh out of labs thing. And these weren't mega hardware systems, these are PCs, missing a lot of cores and things, doing it all in software.
This isn't a question for you, Brandon. I'm Rob Speed. I'm the principal DevOps engineer in iPlayer. So it's just to answer that question, an SD stream is probably about a smidge under 1.5 meg. So with the government saying, oh, you want a minimum of 2 meg, does that sort of give you an idea as to what you would probably need?
You need 50. Okay, thank you.
Okay, thank you very much, Brandon.